I'm going to just do a really simple thing, and the question is, well, how do we add a new configuration option to SU2? So let's say, for example, I'm debugging SU2, and what I want to know is I want to know what the Spilardo Mars source term is at one of the node locations. And maybe I need to do this procedure a lot because I'm working on the transition model for SU2, for example, and so I want to just be able to, in the config file, change which node is being printed so I could watch for whatever reason. So I use Xcode when I work with SU2. So we fork the repository to btracey/SU2, and now I can go into SU2 IDE, and there's the Xcode thing, and I'll open up the CFD project. Okay, so the way the configuration options are in SU2, there are basically 3 important files. So the first important file, unsurprisingly, is configstructure.hpp. And if we look basically right at the top of configstructure.hpp, there's class cconfig. And class cconfig contains fields for all of your favorite options. So if you remember Heather and Andrew's talk yesterday, we have kind SU2, and we can see, if we did a search, we can see the CFL number. So here's one CFL for each multigrid, and there's a whole, all the options live in cconfig. Now, the second important file is optionstructure.hpp, and option structure contains, first, it contains all of the definitions for the enum options. So, for example, here's C-enum solver, which is an enum option for which solver class you're using. And here it lists all of the possible options that you can have for C-enum solver. And here, below that, it has a map from strings to enum solvers. So this is how the config file, when you type in you want the Euler solver, it will then parse, hey, that must mean the Euler C-enum type, so the enum type for the enum solver, and then it'll put that into the config struct. And so this is where all the enum options live, and if you want to create your own enum option, you can kind of use these codes as a basis for your own. And then, even below that, if we scroll all the way down to past all the enum options, there are all these C option classes, which are all child classes of this C option base. And what these C option classes are, if you're just using SU2, you don't need to know. But these contain how SU2 takes the string in the config file and parses that into the config structure as an option. So someone yesterday asked, how do you know, say, what a marker inlet is, or the DV vals? How do you know what all the DV vals numbers means? Well, the best way that you can look is we'll scroll down and we'll find C marker, or marker. So C option inlet, sorry, it's an inlet option. And we can see, hey, here are all the things that it takes, and we can look and see what exactly is being parsed into what. So yeah, you'll have to sort of go between the config file, but we see that the first one is the total temperature, and then the total pressure, and then 3 flow direction parameters. And so that's what the inlet option is. So if nothing else, the source code is going to be accurate, and you can go and look here at what exactly is happening. And you can use, if you need your own, we definitely encourage people to use the option types that are already built in, because it's easiest to have a small number of option types. But if you do need your own custom option for some reason, you can use these custom options, so C option inlet, or C option DV vals, or C option Riemann, to give you sort of a way custom options work. Now, the way most options work, however, is comes in the third. So the third important file is now configstructure.cpp, where we actually have the config class constructor, and later on we also have the setConfig options function. And what this has is it has a number of ways of effectively registering the options for cconfig to use. So we have all these sort of add blank options, and what that is, we're going to add a type that has this name and then whatever parameters in the config file are needed. So an easy one to look at, for example, is to add a double option. So this is adding an option that has a type of double. And so here we're adding the gamma value type, or the gamma value option to the config file. And so this option will have the name gamma, a capital gamma underscore capital value. It's a double, so it knows that it's going to be parsing a double number after the equal sign, and it will store that number into into this field gamma in the configuration file structure. And this last field here is a default value. So if gamma value is not set in the config file, it means that gamma is 1.4. And we can look, so there's also, for example, an add boolean option, where, so restart solution, do you want to restart or not? Well, that has the field name restart solution. It's going to get parsed into the restart field of the config file, and it has a default value of false. The enum options are slightly more complicated because you need to also tell it, so we have a regime type as the name. We want to parse it into the kind regime field of the cconfig. We also need to tell it that regime map that we saw earlier. So given a string, which actual constant number that is. And then lastly, the default is compressible. So somebody asked about that yesterday. What is the default value? Well, here's in config structure.cpp is where you can definitively see what all the default values are. Okay, great. So now let's use this knowledge to do what we want to do. So we want to output the Spaulding source term at a specific node number. So first, in config structure.hpp, let's go add a new config option. So we'll probably want to organize it somewhere more intelligent, but for the purposes of this demonstration, we'll just add it up at the top. So we want the node number, we want it to be an int, and let's call it SA source print. Cool. So now we've added a field to the configuration structure in that definition. And now let's add a way of getting it into the config file. So our type is an int type. So we want to add int option, add integer option. Our string name, we'll call it SA source print. Our option field was what we just added. So that's SA source print, as we just defined there, that integer type. And now we'll make our default value to be -1. So what that'll do is it'll say, well, if the value is -1, that means we're sort of not debugging this, and so let's not print it at all. Great. So the last thing we need to do is if we look at config structure.hpp, it's in the private section of cconfig. And the reason why it's in the private field is because we don't want random parts of the code to be able to change that number. We want that number to be fixed, and now we know no matter what happens, that can't be edited except when we're parsing in the config file. However, we do want to be able to use that value, and so we can't just call the field of cconfig directly. So what we'll do is we will add a method, we'll add a getter method in order to get that value. So we will add that in config structure.cpp, and if we scroll down this code, we'll see somewhere that there are a number of getter methods. Oh, sorry, that's got to be in HPP. I'm sorry. Where all the method definitions are. So, for example, you can see these get ref origins. So we'll add a method that's going to return an integer, and we'll call it get SA source print, and it's not going to take in any values. So we've just defined the function signature for this getter, and now we want it to be an inline function to make it a little faster. So if we go into config structure.inl, we see that there are a whole bunch of inline methods. So we'll add in one of our own. So inline int. It's a function. It's a method of cconfig, and we want it to be get SA source print. Doesn't have any inputs, and we want to return the SA source print number of the config file, of the config structure. Does that make sense to everybody? So what we did, to recap, was we added the field to cconfig such that the data exists somewhere. Then we added a method to access that field, and that went into two places. There was the function prototype in the header file in cconfig, or sorry, config structure.hpp, and then we added the function itself in the inline config structure.inl. So now we have a way, now the function exists, we have a way of getting it, and then lastly we added that option to config structure.cpp, so now there's a way of getting sort of that string that you have in the config file as data in the config structure to use. Great. So now let's actually implement the functionality. So the way, as Annika I think has talked about and we'll be talking more about, there's the solver class, which controls, sort of controls the data, and then it'll send data to the numerics class. The numerics class will actually do the computation. It'll compute the source term, and then it'll bring that value back up to the solver class. So in solver direct turbulent.cpp is where that solver for the turbulent quantities live, and we can go to, so we want the Spilardo Maris, so tserb SA solver, and we want to get the source residual, and because that's what we want to print. And if we scroll down, we see that there's this compute residual term, and so let's add. So we want to say if so we have the config. Sorry, so let's go up. So we see that config is our cconfig type, and so now let's call that method. So let's get SA source print. So we want to know which point do we want to print, and we want to say if that's equal to the current point. And we see up here that we're looping over all of the points in the domain. So if the point in the domain that we're at is equal to the one we want to print, well, let's print the value. And yeah. This right now is solver turbulent direct.cpp. And we're calling, so residual is actually a vector in case your turbulence model has multiple source terms. But the Spilardo Maris, there's only one, and so we're going to get the first element of that residual vector. Cool. So now we hope that I didn't make any mistakes. And now let's install the code again. And this is going to take a minute to install, unfortunately, because we've modified all the header files. So if there are any questions right now while this is recompiling, I'm happy to take them. Yeah.
If you want to add a more complicated option in the config file, what's the best strategy? Copy and paste from somewhere?
Yeah, so I would say your first best strategy is to look at the config types that are there and say, hey, does my config type actually match one that already exists? So for example, there are many formats that are like marker inlet, for example. So a lot of the inlet types have the same basic thing where we need to specify some scalar value and some vector value. And so maybe yours is a scalar and a vector, in which case even maybe inlet is the wrong name for your option, but it has the right pattern, so it'll be parsed correctly. Otherwise, you should just take a look at the different things that are there, and you can see what can be done. And I don't want to say copy and paste, but you can use it as inspiration. So blind copy and paste can be wrong, but like copy the header file, and maybe you'll need to write your own sort of parse function that's there. Okay, so great. So while this is compiling, let's actually add our option. So I constructed a test case for here, which is the NACA 0012 with a turbulent grid. So we can go into our config file and we see, hey, we're using the Spilardo Maris source term and we're computing the direct and all sorts of other fun options here. So now what we want to do is we want to for the source term value, and remember we had called it SA source print, and let's say that we want to be at node number 2845, because maybe we ran the solution before and we saw that that point was going particularly bizarre, and so we want to watch its iteration history, for example.
Is there a particular place to to write that language. You can write that.
So for the purposes of this demonstration, not really, because we haven't been very rigorous about it at all. However, if we look, there are a number of different config categories that are here. So for example, the highest level definitions are right at the top, and then we have things that are the compressible free stream and things that are the compressible and incompressible. So if your option type fits into one of those, then you should add it there. And same thing in the config file and where the different add options are. So both Python and I have my own scripts that will print out we'll do some automatic config writing for yourself. And the order in which it will write those config options is the same as the order that it's in the source file. So it's very, if you're going to push these changes back upstream to the main SU2, you should follow sort of the established conventions as to which category it should live in, because it makes everybody's life easier. Now, if you just need to do the fastest thing possible, as far as the code is concerned, it doesn't actually matter where you add it, with a couple of exceptions. So, for example, there are two DV types. So there's like num DV vals, and then there's a DV vals. And you need to have the num DV vals before the DV vals. So you need to specify how many there are before you actually can get all the values themselves. But for the most part, it doesn't strictly matter what order they're in. But for purposes of code maintainability and legibility, you should try to follow the established conventions as to where to add them.
So on that note, I wonder if you can mention the commenting system, the description config category.
Yeah. I will. I also don't know what I did wrong. Segmentation fault in the compiler? What? I didn't even edit that file. Okay, this all worked last night. This is the live demos problem.
So while that's going, there's a question from online. I'll jump in. There are test cases which are incompressible but are run as compressible in SU2. If you're running low Mach number incompressible flow as a compressible problem, there are some preconditioning things you can do. So can you please talk a little bit about what preconditioner has been used and where in the source code it is present so that I can change it and play around with it? I can jump in and answer this one. We do have a row Turkle low Mach number preconditioning that's available inside the code. And so you'll see this within the mean flow solver along with the upwind method. So if you look in upwind residual, where we're computing the convective terms, you're going to see a number of places where we are computing some of the terms that you need for the upwind or the low speeding preconditioner, rather. Along with that, inside of the numerics class, you'll find a very specific Turkle preconditioning numerical method. And if you go inside of there, what you'll find is a method that looks a lot like the row scheme, except it does have the preconditioning terms. So some things that involve different parameters that you have to compute with each step, so that you can precondition the fluxes at each node, at each edge when you're computing the convective terms. And we have another question. If I wish to print the area of each cell on a chosen face, what would be the best way to do this? Okay. If I want to print the area, okay, so if you want to print the area within one of the methods, probably the easiest thing to look at is, let's say, a boundary condition. If you go to one of the boundary conditions, I find that those are relatively easy to see what's going on. So perhaps if you go to the Euler wall boundary condition or something like that, what you'll see are a bunch of getter methods for things at nodes, things on edges, and including one of the most important ones is the normal. So if you go to one of the nodes on the surface and you say, geometry, arrow, etc., get normal, what you're going to get is the area of the dual face associated with that node. So it's an area vector. So it's a normal vector that has the area as the magnitude of the face. And so that's one way to get a look at kind of the area of a face. And whenever you get the normal vector in the code, capital normal with an N, a capital N, that's giving you the area normal. So it has magnitude that is the surface area of the face. And so typically you'll see
after you get the normal, we often find the unit normal by computing the magnitude of the area and dividing it. So that's very typical. You'll see that in most of the boundary conditions.
And I just want to add to that the file you're looking for is called solver_direct_mean.cpp.
Yeah, so Aniket asked a second ago about so the comment structure. And I was going to do a gimmick with that later, but I can just talk about it now. It's probably better anyway. So if we look at config structure.cpp, we see here that there is all of these descriptions and config categories and stuff. And strictly, this isn't necessary as far as C++ is concerned, but as far as having nice ways to interact with SU2, it's definitely necessary. So if we see, there's this config category, problem definition. And if we look in the config file, there's this problem definition. And I know both I believe the way Trent's script works and the way my scripts work is that I will print out this header, but it will use the text from this config category. And then there's a comment on what it means. And same thing now when there's this regime type, there'll be a comment above it that says adjoint type and things like that. And so what this structure allows us to do is allows us to parse config structure.cpp in an easy way that doesn't require us writing a full C++ parser. And it allows us to get what the options are and sort of what they're supposed to look like. So when we added this SA source print option, we also should add a description. So it will say, for example, print the SA source term at a given location. Or we'll call it point ID. And so now we've commented it, and now when this gets pushed up to the master, or to the develop and then to the master, we can rerun the parsing script such that your option will also be added into the suite of things that's easy to use and work with. Okay, I'm not sure what I've done wrong. So unfortunately this won't work, but if you were to run SU2 CFD, now you would see that it's printing at specific values. I'm not sure what's happened, but that's okay.